your screen to let you know that this meeting is being recorded. So as Jaron goes over the slides, I'm gonna ask him to please pause every few minutes or few slides and take questions. You're welcome to ask questions at that time or leave your questions to the end. I would ask that you please mute yourself during the call, just so we avoid any background noise. We have about 50 people in this call, which is great. We would love to hear from all of you, but please keep your questions to the time when Jaron asks for questions or to the end. And then feel free to use the chat box if you're having issues, if you're not hearing anything, or if you lose the visual. Also use it if you're not able to use your microphone to ask questions, and I'll be happy to ask your question on your behalf. So that's all I have. If everyone is hearing me all right and is able to see Jaron's slides, I'll pass the microphone to you, Jaron, and I'll mute myself.
Great. Okay, well, thank you. Boy, this is a lot more people than I expected. I wasn't sure if we should expect a huge turnout because it's a video conference, or if we wouldn't expect to see many at all, but it's great to see a good turnout. So I'm just going to jump right in. Thanks, Simon, for the tips on everybody muting, and as we dive in here, normally if I were in front of all you guys, I would just say, yeah, like if you have a question to raise your hand, but since we're video conference, it's a little tough. So I'll try to break at some natural points in the presentation as we move through and ask if anybody has any questions. So let me see, we can get my mouse here. Okay, so a little bit about me. I'm Jaron Brown. I've been with NHC since 2008. The last 7 years or so, I've been working in the lab, and I did a master's degree in civil and environmental engineering at BYU. And a fun fact about myself is I grew up in Clinton, Mississippi, which is the home of the Mississippi River Basin Model, which was built in the 1940s by German prisoners of war from World War II. They used the prisoners of war for labor. They built this basin model. It's it covers the whole Mississippi River Basin, roughly a third of the continental U.S., and it's over 80 acres of land. And when I was in high school, I ran cross country, and the land where the model is now derelict is where we ran our cross country races. So I remember running past and looking through this chain link fence and seeing this old derelict model, through the brambles and fences and stuff, and wondering what it was, and had no idea I would ever be involved in physical modeling myself. But a little bit about NHC. We're a water resource specialist firm. About 200 employees with offices up and down the West Coast and across Canada. The bulk of our work is in the US and Canada, with some projects in Asia and South America. Even though we're here talking about physical modeling, by no means is that what NHC does strictly. We have all kinds of skills in different water resource areas: hydraulics, hydrology, river engineering. That picture on the top right is yours truly doing some bathymetric survey mapping on I think that's the Stillaguamish River, with my colleague Andrew flying the drone there that you can see him on the bank. Okay, so, kind of getting more into physical modeling. Our laboratory facilities are here in Seattle, also Vancouver, BC, Edmonton, and Montreal. And each one of our labs is pretty much fully self-sustaining in terms of the custom fabrication that each model requires. Instrumentation is often done in-house. There's not always commercially available instrumentation for the applications that we need, so we do a lot of creative problem solving for analyzing and getting data out of the models. And physical modeling is about 25% of the total workload at NHC, and we're the largest commercial facility in Western North America. Um, the areas where we might typically expect to do a physical model are dams and spillways and intakes. We get involved with physical modeling with sedimentation, especially around bridge piers and scour, big bridges, which I have a couple examples that I'll show later on in the presentation. Pump stations are very frequent physical model studies. Municipal structures like drop shafts, and this picture in the top right is a drop shaft for a stormwater conveyance system. So those are kind of the areas. Also, fish passage, fish ladders, and that sort of thing. So any of those areas will typically, they're complex enough, and oftentimes we'll be looking at a physical model to help with the design or the assessment. Again, even though we're here talking about physical modeling, there's most projects involve this day and age numerical modeling as well, and the key point here is that they're often used in concert, and whatever, whether it's 1D, 2D, or CFD modeling. Folks at NHC have experience with a wide array of these numerical models that can help either inform a physical model or vice versa. So I'll talk about some of the ways that physical and numerical models work together as I go through some of the examples that I have. Okay, so this slide shows this kind of spectrum between the simplest 1D, a HEC-RAS model, for example, up to physical models. And this is a spectrum both in terms of simplicity, also ease of use, and general cost to develop, or kind of speaking in rough terms. And it's also a spectrum of simplifying assumptions. So one of my colleagues, whose name I see on the participant list here, has a quote on his door from George Box, who's a statistician, that says, every model is wrong, but some models are useful, or something like that. I guess I'm not quoting, I'm paraphrasing. Any model is wrong because of these simplifying assumptions that it makes. But depending on what those assumptions are and how the user understands those assumptions, they can be very advantageous in terms of simplifying and making the computations very lean and efficient, like a 1D model, going up to a physical model that makes very few assumptions. It just is what it is, and it's the same as the prototype. So where there's complexity and high risk, then those simplifying assumptions become maybe more risky, and that's where we start to get towards the right-hand side of this spectrum. So the way physical modeling works is we build a scaled-down replica of the prototype. In physical modeling, we refer to the model and the prototype as the real-world object or project site. And the scaling is done geometrically, but based on similarity laws. So there's certain characteristics of water that don't scale, such as surface tension, viscosity, gravity, time. These things don't scale in the laboratory relative to real life. So we have to make sure that the ratio of these forces in the model is appropriate and not going to cause these forces to create an undue influence in the model. So the scaling is very well developed. There's very well developed methodology of how to pick the geometric scale and then check that surface tension and viscosity and these other factors don't affect the model adversely. But once the model is there and scaled correctly, what you see in the model is very much what you'll see in real life. This is a picture of Long Lake Dam, which is one of the examples that I'll go into in more detail here in a little bit. But some of the advantages of a physical model is you have a direct visualization of the flow field. So you're not looking at cross sections or profile plots or anything like that. You're just looking at the actual flow, and with using clear acrylic and dye and cameras and time lapses or high-speed cameras, whatever you need, you can really see what is going on and what will happen in the prototype. So that's why it's a useful tool. Then, okay, so as we go through the presentation, I'm going to talk about kind of models that fit these three categories of being useful for design or for assessment or for demonstration. And any model will have some overlap in each one of these categories, but these are generally where they break down into kind of their general purpose. A design confirmation model would be used where maybe it's a pretty standardized design. I'll talk about a Labyrinth spillway here in a few minutes. That the guidelines for design are well developed, but there's a high risk and or a high cost associated with the project. So having extra assurance from a physical model may be what the driving purpose behind people coming to us. Or design development, where there's the guidelines are less straightforward or undeveloped completely, and the physical model can be used to just come up with solutions that are novel. And I'll go through some examples of that. Then there's assessments, where we're looking at maybe a prototype that has some kind of problem, but it's unknown what the source is coming from, whether it's some sort of vibration issue or cavitation or sedimentation. And so we'll build the existing condition model and then see how the physical model replicates the problem and then start taking steps. And then lastly, we use physical modeling for demonstration purposes, where in those cases, maybe the hydrotechnical questions aren't beyond the easy reach of numerical modeling, but having a physical, tangible object that people can come gather around and look at is where a physical model can kind of pay for itself or be a valuable tool in sparking conversations. And so through the presentation, I'll address each one of these various topics and how a model, kind of fits within each one of these purposes. So I'm going to talk about some spillway models, some pump stations, a reservoir, a clear well, and some fish hatchery model that we did, and then some models that were more kind of demonstration or public relations, and then end with bridge hydraulics. So any questions so far? I guess now's a good time to break and ask if anybody has anything that they want to ask before we jump into specific examples. Okay, good.
And
I don't know. Oh, yeah.
Just remember to unmute yourself before you speak, before you ask questions. By default, I think I muted everyone, so please make sure you unmute yourself if you have any questions.
Great. Good. Okay, yeah. So, all right. If no questions, then we'll move on to our first example, which is, I already mentioned this Long Lake Dam. It's on the Spokane River, west of the city of Spokane, Washington. And this model fits into the design development category. So the owner of the dam, Avista Utility, had a water quality issue from the dam, a TDG issue, total dissolved gas, which is caused from this highly aerated flow coming down over the spillway. I hope you guys can see my cursor on the screen, but so there's this highly aerated flow that comes down the spillway and plunges into this deep pool, and then the dissolved oxygen goes the DO levels go through the roof, and it's actually super saturated with oxygen, and it's a water quality issue downstream. So we built a physical model in our laboratory a few years ago to help figure out what can be done about this TDG. And this is the category where there aren't really straightforward guidelines, a manual somewhere where you can just look up and say, this is what you need to do. So we used the model to test lots of different things. You can see these different baffle blocks here glued to the spillway at we tested different spacing and different configurations of those energy dissipation blocks. We looked at this spillway deflector here at the toe to keep the water from plunging down and more skimming across the surface. We looked at shaving off this knob here on the river left and using that material to fill in the hole that is at the toe of the dam, which the oxygen goes into the water at depth. So if there is no depth, it's not as big of a deal. So using the model to kind of develop a design is kind of what we did with Long Lake. And there's a picture of it under construction with the preferred design, or the settled on solution, which did not involve the teeth on the spillway. It was just the deflector and shaving off the knob and filling in the hole. So that's, a good example of where we can step through lots of tests in a fairly efficient fashion to look at how that water, kind of the way that it flows after it exits the spillway and directing it the way we want. Another design project, it's more of a design confirmation, the Almaden Dam Labyrinth Spillway. This view is taking as if you're standing, or I guess flying above the reservoir looking downstream. Almaden Dam is owned by the Santa Clara Valley Water District down in California. They provide water to San Jose and kind of that south end of the San Francisco Bay Area, Silicon Valley. And their existing dam, so this is looking, we're above the reservoir looking downstream, and over here on our left at the top of the picture is the crest of the dam. It's an earth-fill dam, and then there's an existing chute which had an OG spillway, which was their emergency overflow. And the existing spillway was rated at 7,500 CFS with 3 feet of freeboard over the dam crest, or below the dam crest. So Santa Clara Valley Water District had a hydrologic study done, and the probable maximum flood for the site changed from 7,500 CFS to over 23,000 CFS. So they had to figure out a way to pass almost 4 times the flow while maintaining the same head requirements of 3 feet of freeboard at the dam crest, so they didn't overtop the dam. And having a limited footprint to work in, came up with this Labyrinth spillway design, which Labyrinth spillways are one of those things that are fairly straightforward, I guess, or there's straightforward guidelines on how to design a Labyrinth spillway in terms of the length of the weir crest and how many cycles. And so they designed the Labyrinth spillway and did some CFD modeling, and then came to us to confirm the CFD model and also look at sizing the chute. So just because it's an expensive project and high risk, they wanted extra assurances that the design would work and not overtop the dam. This is also a good example of how a physical model can be used and wind up paying for itself, because one of the secondary objectives with the physical model study was to look at the size of the chute downstream of the spillway. It's not obvious here from this photo, but this is on the right of the chute is the valley wall, and it's a mountain that goes up quite steeply. So the smaller that they needed to excavate that chute, or the less they needed to excavate, the more money they'd save. And we, with the physical model, with just a couple hours of a technician's time in adding plywood to this right-hand side of the chute wall and the floor, raising the floor up and bringing the right chute wall in, showed that the chute could be reduced and saved them a couple of $1 million in excavation costs. So even though the model was built primarily to confirm the CFD and help everybody feel good about the design of the Labyrinth spillway, it was a nice it was a nice tool to use to look at these other aspects of the design and help kind of optimize things. Okay, so now we're going to move into talking about pump stations. I guess before we do that, does anybody have any questions about either Long Lake or Almaden Dam, or have anything they want to say about? Yeah, have any questions? Good. Okay. So pump stations are, typically in our world, civil engineering world, water treatment plants, wastewater treatment plants, stormwater, even nuclear power plants with cooling pumps and cooling systems. And what we're looking for when we build a pump station model is one of three things. We're looking for non-uniform velocities as it enters into the pump column. So we build the pump columns out of acrylic so we can see through them. So we're looking for this top diagram up here, hot spots within the pump column. And we're looking at vortices. We use dye to hunt around and see if there's any vortices forming from the surface or from a sidewall or floor. And then we also look for something called pre-swirl, which is what this video shows. These are pre-swirl meters. So these are these meters when they're spinning around, there's pre-swirl. And what that is where, so a pump is designed to have water approaching the impeller parallel to the axis of rotation of the impeller, which is this bottom diagram here in the lower right. And if the layout of the pump is, the layout of the pump station can affect the way water approaches the pump and cause it to come in at an angle relative to the axis of rotation. And what that pre-swirl does is cause a differential load on the impeller as it spins around. So it's more resistance on one side and less on the other. And it causes, all three of these things, the velocity fluctuations and vortices, all of those cause problems with the pumps where they reduce efficiency and can cause cavitation and noise and create maintenance issues for the pump plant managers and owners. So our first example that we'll talk about, this EL475 pump station, was built here in our Seattle office, or Seattle lab. The East Low Canal comes out of Banks Lake in kind of north central Washington, and then the canal flows south and east across the state and is used for irrigation purposes. And it's a pretty big canal. It's 50-foot bottom width and up to 18 or 20 feet deep when it's at maximum capacity. And every 15 or 20 miles, they have a pump station that pulls water out of the canal and sends it on to a distribution system with those big center pivot irrigation. So they were proposing to build a new pump station off the canal and needed to show that the conditions within the pump station met HI, the Hydraulic Institute, met criteria so that the pump manufacturer could install a pump and know that the flow conditions, they could vouch for the lifetime of their pump given these certain flow conditions. So because of the size of the canal, 50 feet wide at the bottom and 20 feet deep, it was way too big to try to build in the laboratory at the scale that we needed in order to look at pre-swirl and velocities and these sort of things within the pump columns in these individual bays. The canal would have needed 2,000 CFS in our laboratory, which is just way too big. So instead of building the whole canal, we did a CFD model of the canal to establish the inflow characteristics within the physical model. So this image in the top right is a part of the canal. The flow is from bottom towards the top here in the canal. And then see how the flow kind of waits until the last second before it gets drawn into the pump station. So we knew that our physical model couldn't contain the whole width or even a reasonable part of the canal. So we just, the black line here is the outline of what our physical model contained. And then we used plywood and perforated plate and a velocity probe to calibrate our physical model to the CFD model to make sure that the inlet velocities and intake conditions were what the CFD model said they needed to be. And then once we had that part done, it was kind of business as usual with the pump station, with looking at the pre-swirl and the vortices and the velocity balance within each individual pump bay. So that's an example where the two work together. We have a situation where CFD modeling played its role, and then the physical model came into play. Here's a nice video of a vortex forming. This is looking upstream through the back wall of the pump station at the far, I guess, our right, but left as you're looking in the direction that the water comes in from the canal. And that vortex, without being in a lab environment with acrylic walls and dye, you would never know it's there. But since that's what the purpose of the physical model is to look for things like this and take preventative measures to either keep that vortex from forming in the first place, or at a minimum keep it from entering into the pump column. Okay, let's talk briefly Clearwells, reservoirs. We've got 50 people or so in the room here, so I'm not sure what the balance between municipal and open channel type engineers are amongst the crowd. But a Clearwell reservoir, they're basically in water treatment plants to improve contact time with the disinfectant, and the goal within a physical model is to minimize short circuiting and look for dead flow zones and figure out what the design needs to be to keep the water moving slowly but steadily through the clear well. Example that we'll talk about is the Earl Schmidt filtration plant down in Santa Clarita, California. A 56 million gallon per day filtration plant, and the physical model study was performed to improve the disinfectant contact time. There's a 1 to 12 scale, so every inch in the model is a foot in the prototype. And I included this one in the presentation because the physical model wound up finding something that we didn't know. And what I mean by that is there was fluctuations with the way the flow was coming over a weir into the model that was causing these fluctuations, which if you had just looked at it in a CFD model, the tendency would be to say, well, are these fluctuations a model instability, or are they real? And kind of have some questions on, what is this thing that we're seeing, this phenomenon, assuming that it actually replicated those fluctuations at all. So, even though the model was designed and performed to just look at the time that water took to make its way through these labyrinth baffles, it wound up finding this other problem that we didn't know we needed to be looking at, and then take measures to figure that out. Okay, so one thing I didn't measure. Oh, how about we pause for questions? I'm going to drink some water, and if anybody has a question, feel free to unmute and call it out.
Hey, Jaron, this is Corey. We have a couple of questions from the chat window. The first one was about the Labyrinth yield. Did the physical model of the Labyrinth yield different results from CFD?
Oh, the Labyrinth Spillway, Almaden Dam. No, it was very similar to the CFD results. I'd have to go back and look at the study, but I want to say so we developed a rating curve for the weir, discharge to head above the weir, and it was within a couple of tenths of a foot. Both, the CFD to the physical model were within easily half a foot, less than that. I want to say 2 or 3 tenths at most. So.
One more question from the chat window. How long does it take to build a physical model?
Yes. Well, they can vary. A big, complicated model like Long Lake, or one of those big dam spillway models will be maybe 6 to 8 weeks of construction, and then pump stations are generally 3 to 4 weeks. They're oftentimes smaller, and this next one that I'm going to talk about was just done in a matter of a week or less. Well, not one of these next few ones, kind of on the quick and dirty end of the scale.
Thanks.
All right. Anything else? Cool. Okay, so I didn't mention in my intro that my undergrad degree is in biology. I went to BYU Hawaii and studied biology. So whenever we talk about fish hatcheries and the habitat type improvement projects, then those are the ones that I get most excited about. Okay, so this is the Soos Creek Fish Hatchery. It's a Washington Department of Fish and Wildlife project on Soos Creek, which is a tributary to the Green River, just right here in South King County. And the hatchery is, okay, so this view on the left is from Google Earth, and the flow is from bottom left to upper right, and the hatchery is on the left side of the creek on this kind of low-lying area that floods every 2 to 5 years. And a few years ago, they had proposed basically moving the entire hatchery. It's really old and outdated, and as part of the upgrade, wanted to move most of the facilities, the intakes and the rearing ponds and the whole thing over to this high ground that's on the right and upstream from where it used to be. And part of that involved redesigning the intake. So they pull water out of the creek to run through the hatchery for the ponds and the hatchery purposes. The existing hatchery had a major sedimentation issue with their intake and needing to dredge out the stream to keep their intake clear on an annual basis. So we built this physical model mobile bed, so the sand was scaled geometrically to the prototype, and looked at the intake configuration for the new pumps in order to develop a self-cleaning intake. And I included this as an example in this presentation because it was really illuminating to me in terms of it was one of the first physical models I worked on, and it became clear like how useful of a tool it can be to rapidly, it doesn't have to rapidly look at different options in order to optimize a design. So, just little chunks of acrylic or little pieces of plywood, and playing with the wing wall configuration or the sill below the intake, and looking at what causes accumulation and what causes it to just keep flushing through and be self-cleaning. And so we just we had the structural and mechanical engineers who were charged with designing that intake structure, and they came into the lab, and together we just played around basically with the different pieces in order to watch that sediment flush through and or accumulate and know what not to do. So another one with the kind of a fish habitat type component was this wastewater treatment plant in Montesano, Washington. The river adjacent to the wastewater treatment plant was eroding this bank and threatening to capture the water treatment plant. And it was almost an emergency measure, an emergency project. We have to do something now. We can't wait for permitting to build in the water below ordinary high water. So the design engineers came up with this idea to build these log jacks. So these are these, 2 to 3 foot logs, diameter logs with giant boulders in the middle, and they're lashed and chained together in sort of a tetrahedron shape. And pile those up on the bank, and then in the summertime when the construction window was available, and then if and when the following winter the river eroded that bank more, they would fall in and protect the bank. So the question was asked, how much does a physical model cost, or how long does it take to build? This is the very end of the spectrum that's quick and dirty, meaning it was built just for our understanding, this novel idea of these jacks on the bank, and then they're going to fall in. Are they going to roll? Do they just kind of flop like a half a turn? Do they take the jacks behind them with them? Like, these are the questions, like, how does this work? That building a physical model was just a handy tool to just kind of get a visualization for what would happen. And then kind of get a feel also for the reduction in velocities behind the log jacks. Once they fell in, are the velocities and the shear stresses on the bank going to be reduced to halt the erosion? Let's see. So I think our next category, I'm going to skip this one in the nature of time. And address, I see a comment in the question, is the Soos Creek headwater pulled only from the Lake Young's reservoir? Soos Creek is, no, does not interact with Lake Young's, to my knowledge. It's, there's a number of tributaries that drain Kent and Maple Valley and come together before it makes it to the Green River, but to my knowledge, there's no interaction with Lake Young's and Soos Creek. Any other questions? Okay, great. Okay, so our next topic is this idea of physical models that are built not so much to answer complex hydrotechnical issues, but to answer more, or to provide a hands-on tool for stakeholders to come and see and visualize what is being proposed. So a couple years ago, we had this project involving the Puyallup River, where the proposal was to remove sediment from the river as a flood reduction measure. And the number of stakeholders involved in a project like that are many. There's cities adjacent to the river, City of Puyallup, Graham, Ording, Pierce County, lots of government agencies from a from a regulatory standpoint. So the this model was built not so much to answer questions about how sediment removal would affect floodwaters, although that was, it was interesting to see and to look at, but it was more built as a conversation piece and to have meetings, people come out and see the effects of the project. You can, in a demonstration fashion, here's existing conditions, and then if we pull out this amount of sediment, here's the change in water surface elevation. Another example of that one would be the Trinity River project that we did. This was up in our Vancouver, BC laboratory. Trinity River flows through downtown Fort Worth, Texas, and the Army Corps of Engineers had proposed building a flood bypass channel. So you can imagine a big bypass channel cut through, basically a downtown corridor, creating bridges where roads are traveling over flat ground. And how many stakeholders would be involved in something like that? You've got transportation people and parks people and city and county and just lots of different concerned people wanting to know about the project. So the Army Corps of Engineers hired NHC to build this scale model. And this one would be at the far end of the spectrum in terms of cost and making sure that every detail looks as much like the prototype as possible. So like the shape of the bridge piers and these artificial trees planted along, the proposed bike paths, and making this thing as easily interpreted by the public as possible. Because what they did was have us build the model and then come up and film the model and interview designers and people involved in the project so that they could inform the public on here's this proposed plan and here's what it's going to do. And so a lay person can look at this and recognize, well, that's the bridge near my house, or, and really get a feel for what the project entailed. This model is also interesting in that the physical model, even though, again, not built for hydrotechnical, complex question or answers, it was built, within the first day of running the model, it became obvious that the bypass channel was much bigger than it needed to be. And so they could reduce the overall size of the bypass and still get the same benefit from a flood reduction standpoint. And that saved the project tens of millions of dollars. And, the model paid for itself many times over just by, this sort of tangential question that got answered. All right, so pause real quick again. I see some questions here in the chat. Let me make sure I get up to the top of them. What did the Montesano model predict? So that was the one with the log jacks that fell into the water. We did show a reduction in the velocities up behind the jacks after they fell in, and felt pretty confident that the associated shear stress along the bank would be reduced and keep that erosion from halting, or keep that erosion from going forward. It would stop that. So yeah, that was, I don't know if that answers your question, James, but hopefully that's kind of what you're asking about is how did those jacks affect the overall erosion? Hey, Bob Elliott, answering some questions for me. Yeah, the headwaters of Little Soos Creek are at Lake Youngs. Okay, good to know. The grass in the Puyallup model, that's actual grass. So it was a mobile bed model built of sand, and we actually planted grass. Just to be honest, I can't remember why we planted grass. I think just for fun. So we had a little grass in the model for a while. Let's see, anything else? Okay, I think that's the bottom of the questions. Okay, we're at 12:48, and I've got one more category to go through, bridge hydraulics, and then the presentation will be done. So bridge hydraulics, there's tens of thousands, hundreds of thousands of bridges in the world, and most of them don't need a physical model study. But some of these great big bridges, with just the huge amount of cost and risk associated with the project, the clients will come to us for a physical model study to look at scour around the piers mostly. So there's some examples: the Portman, Patella Bridge, Pitt River Bridge, and then the Padma River Bridge, which I'll talk about. So these are some photos of mobile bed models with bridge piers. We don't build the deck and the suspension or whatever, is the superstructure above the piers. We're just looking at the scour around each pier. So the model is simplified that way. The Padma River Bridge. So the Padma River is in Bangladesh, and it's formed by the confluence of the Brahmaputra and the Ganges River. And once those two come together and form the Padma River, it's the third, but nearly tied with the second river in the world in terms of discharge, second biggest in the world in terms of discharge, and it's the number one river in the world in terms of sediment load. This river carries a humongous amount of sand. So here's an aerial image of the bridge site, and the bridge is, so for a sense of scale, this is 6 kilometers from one abutment across the other. There's 43 different piers and 150 meters between spans, or the spans are 150 meters between the piers. And then, so NHC was retained to look at scour around the bridge piers and also the river training works, which is this protection along the upstream right bank to keep the river from flanking the bridge. And that was some 14 kilometers of protection to keep the river within the bridge span and not overflowing the banks. So 2 different physical models, well, actually more than 2, but the bridge scour model was 1:80 scale and used crushed walnut. Sometimes the scaling doesn't work with sand. It's, if you're using sand in the prototype, you can't use sand. If it's sand in the prototype and you're 1:80 scale, you can't use sand in the laboratory. So we use crushed walnut. It's finer, but has a similar specific density and specific gravity and that sort of thing that makes it behave the same. So we used crushed walnut there and found up to 22 meters of scour for these piers. And then built what was called the comprehensive model, which was built in Bangladesh using local engineers and local labor to look at the scour around the river training works. And that's this 2D model here. This is the river training works on the left, and then the scour hole that was computed that matched the physical model. And in the physical model, they showed that the scour would be up to 67 meters deep. So tremendous amounts of sediment movement and a tremendous amount of engineering involved to keep the river contained and keep that bridge safe where it needed to be. Okay, let's see. That's kind of it as far as examples. We're coming up on our hour-long marker here. So to kind of summarize, why do we do physical modeling? For these complex situations and where there's a high amount of risk or uncertainty. They're very useful tools, even if they're not primarily built for stakeholders and a communication. Even if it's not a news crew coming to film the model, they're still really valuable in terms of this tangible thing that people can see and understand. And then let's see, the cost of the model, that's oftentimes a major consideration. It's that Montesano log-jack model was at the far end of the spectrum. We just built it basically for our own in-house understanding. It was $5,000 or $8,000, but then a model like Long Lake or the Padma River, Trinity River can be multiple hundreds of thousands of dollars. But with the overall savings to the project, the physical model can often pay for itself, like I mentioned in those examples with sizing the chute for the Almaden Spillway and the sizing the bypass channel with the Trinity River model. So that's kind of it. I got time for questions. I see there's a couple more coming in on the chat box, so if people want to just keep typing in questions, I'll stay here and keep answering. I also have Darren Hinton and Tom Demlow, who are both work here at NHC and are involved in physical modeling, so they can correct me if I get anything wrong. Let's see, the Padma River, so this is a question. Padma River Training Works scour hole, what was the numerical model used? That was there was two numerical models. One was River 2D, and then a Telemac 2D models. So both of them replicated that roughly 60 to 70 meters of scour along that River Training Works. Let's see, did I skip any? Darren answered the question about the grass. Then above Darren, so, how the jacks behaved on entering the water, or at least what the model showed. Yeah, so that was interesting. We weren't sure, once they fell down into the channel, would they just keep rolling down the slope and eventually make it down into the thalweg, or would they just kind of flop once and stay right there? And they showed basically it was just like a single roll. They didn't go too far, which, being a big tetrahedron and very dense with that boulder in the middle, I think it was a 4-ton boulder. I could be wrong, maybe it's 2. But it just, they didn't go far. So the jacks basically stayed right there. All right, let me scroll down here. Oh, from Tom Bean, what does social distancing look like in the physical model lab? Business as usual. No, I would not say it's business as usual. It's definitely tough. Our Seattle lab is closed. There's different provincial laws in Vancouver. They're operating under different governmental guidelines than we are. So our Vancouver lab, they're working 7 days a week with 2-man shifts. And, there's one crew who works Monday through Thursday, and then another crew who works Friday, Saturday, Sunday, and they clean the tools between shifts, and it's a little bit reduced. Well, for sure it's reduced in terms of the staffing, but it's also coinciding with just timing between models and stuff. So it's, we're making it work. It's not ideal, but, you make it work. All right, let's see. Okay, there's a comment about grass on the Puyallup River model. Yeah, okay, answered the question about Montesano. Okay, so if anybody has any more questions, feel free to type away or unmute yourself and chime in. We'll be here till the end, but that's pretty much all I have to share.
Okay. Well, thank you, Jaron. Appreciate everyone's questions and inputs. Got a couple more minutes. If anyone has more questions to Jaron, please unmute yourself and pass them around. If not, I guess we'll just pause for a couple of minutes and see if anyone has more questions.
Hey, how's it going? This is Dan Shapiro. from Seattle. Can everyone hear me?
Yeah, I can.
I was wondering for the Scour model, is it like reevaluating, like because as the model runs, the channel is being deformed. So is it recalculating what the new velocities and everything are going to be each time, or?
Are you referring to the 2D modeling?
Yeah.
Um, that is not my area. Maybe Darren could chime in. I don't know if Darren's still on the line, but I actually don't know how those 2D models work with Scour. I believe that's the case, that they're looking at the bed deformation and then recalculating everything, new depth average results. But I'm not sure how it works. I don't really do much 2D modeling, I'm afraid to say. If anybody else is here in the conversation, we've got a good crowd here. So if anybody else knows the answer, feel free to chime in.
Cool. Well, thanks for taking a stab at it.
Yeah.
So, Jaron, I know we talked earlier this year about doing a tour of the lab, and I know you guys were working on a physical model that you wanted to show to those on the call. Is that something you guys still interested in doing? Maybe next year?
Yeah, definitely. That was the original goal here, just for everybody's information, was to do the brown bag in our laboratory and talk about modeling, and probably a shorter version of this presentation, and then go out and look at some of the models we actually had. So yeah, that's definitely something we can put together once we're all able to be in the same room.
Yeah, definitely. And we would be happy to work with you and with NHC to organize this, hopefully sometime soon.
Great.
So with that, I think we're on the hour. So thank you so much, Jaron. Thanks everyone for joining the call. I think we had a really good turnout, and appreciate everyone's taking the time. And we'll hopefully talk to you next month.
Great. Thanks for having me, and thanks for tuning in, everyone. Stay safe out there.
Thank you for the presentation.
Thank you.
All right. Take care, everyone.
See ya.